Assalamu alaikum wa rahmatullah, and good afternoon to all of you, our beloved viewers of the Voice of the Cape's YouTube page, as well as the VOC's Facebook page. My name is Imaad Adams, and it gives me a great honor and pleasure to be hosting this particular program, and that is the Voice of the Cape's Matric Revision Program for 2023 in collaboration with Futures Academy SA Online High School. So today, we are honored once again to be engaging with Brother Imaad Isaacs, who is from Futures Academy and he is the head there. And he will be giving over and facilitating today's session, which will be dedicated, of course, to the subject of mathematics, paper one, and continuing from where we left off the day before yesterday, and that is with regards to factors, inshallah. So without further ado, as a reminder, once again, as I always remind you, our beloved viewers, if you have family members, friends, neighbors, people out in the community who you know are currently in Matric right now, please forward and share this link with them from the VOC's Facebook page as well as the VOC's YouTube page in order that the matriculants out there who are preparing for their trial examinations will be able to effectively prepare for the examinations as well as succeed in all of their matric endeavors for the trial examinations as well as for the NSC exams. Without further ado, inshallah, we hand over to Brother Imaad Isaacs from Futures Academy, who will facilitate today's session, and that will be pertaining to mathematics preparation for paper one, inshallah. Bismillah.
Okay, good afternoon to all our viewers, grades 11 as well as grades 12. We are continuing with our section today that is focusing on, although it's labeled collectible marks, we should be busy with the section on functions. Right, so that's exactly what we'll be doing, and that's exactly what we'll be looking at. Now, functions is a fairly large section in terms of the matric exam. We can see that it takes up 23%. And of course, the work that you do in functions are also valid and relevant for the section that you engage in calculus with, okay? Because obviously calculus focuses on specific types of functions, that being polynomial functions, particularly of degree 3 and higher, of which degree 3 is what you study in the matric curriculum. Okay. So that will be our focus today. So we're going to build up the section. I think in the last section, we touched on domain and range, and we looked at number sense. And we also looked at, let's see what we looked at. We looked at the nature of roots, and that was what we tackled in the last lesson. Now, the nature of roots is very, very relevant to the parabola, which was your quadratic function. And in summary, we looked at calculating the discriminant and how to determine and speak about the roots or determine its nature without actually having to solve for the roots, okay? We came about by saying that delta is equal to b squared minus 4ac. And then we also concluded that if delta was positive or 0, the roots will be real. But if it's real, it will have equal roots. If it is greater than 0, it will have unequal roots. And then we also look at whether delta is a perfect square or an imperfect square, and that will help us determine whether the roots are rational or irrational. We also then covered the case of imaginary roots, and we also showed you what that looks like graphically. That's going to be a parabola that does not touch the x-axis at all. In other words, it doesn't intersect there. Okay, so moving forward, and then we've done quite a few questions of the nature of roots. Now, today we're going to be looking at functions. Now, in the previous lesson, we went into quite a bit of detail as to what you need to know with respect to functions. We spoke about the different levels of the questions in the section on functions. We also looked at, in the tick list, what you must be familiar with, right? Now, when we teach this in school, we will go over a very specific definition of what a function is, and that is, it's a special type of a relation. Okay, so if you think of what's a relation, you would have learned in school that a relation is a map from one set to another. Okay, and then when we talk about a function, we say that it is a well-behaved relation. In other words, it's a relation. That means it's a map from one set to another set. But then when we say a function is a well-behaved relation, it simply means the definition of a relation is relevant, but well-behaved means that we're going to define it more specifically. And that means in that map from one set to the other set, every element in the source set, sometimes called the domain, is mapped to exactly one element at most. Sorry, not exactly, that's the wrong word, but to say at most one element in the target or the codomain. Okay, so that's just terminology. Now, in terms of the matric examination preparation, we're not going to bog you down with what the definition of a function is, although it's relevant and you must know it, because you're going to be required to do things like the vertical line test and the horizontal line test, and then you must always take that back to the definitions of a function. Okay. Now, where the marks come from? The marks come from being able to work with functions graphically, particularly graphically. And that's why the section is called in the matric paper, Functions and Graphs. The other thing I must also remind you of is that in our last lesson, we spoke a little bit about how do we represent functions. Now, a function may be represented in 4 ways, and those 4 ways are, number 1, graphically, number 2, or let's just place it here and write it on the whiteboard. Number 1 was, sorry, I just want to adjust the screen a little bit more. Okay, the one way of representing functions, okay, the one way was, let's start by the easiest way that you are familiar with. It's algebraically, right? This means by means of a formula. So this means if I have a straight line, the straight line's example can be y equals 2x or 2x plus 3, etc. That's algebraically. That means with a rule or a formula, okay? The second way to represent a function is graphically, okay? The third way to represent a function is in a table format, in a tabular manner, okay, or tabulated. Now, the table manner is what you've been using throughout your high school career. When you started out, you said there's a table, 1 row with x, 1 row with y. If this is the x value, what will be the y value, right? Or whatever you want to make the independent and the dependent variables. And then the fourth way of representing a function is we've got algebraically, graphically, in a tabular manner, and then verbally. Now, from your English class, you must know that verbally means using words. It does not mean speaking, right? So a letter that is written is also a verbal letter, right? So when you speak, we refer to that as orally. Okay, now let's move forward a little bit. Okay, that's the 4 ways of representing functions. So what I'd like you to do is we'd like to just build up a quick summary. And let's start with a table. Let's say we have 4 functions. So the rows will be 5 rows, okay? And the number of columns, let's say we have a type, we have a shape, we have an example, and we have 2 movements. So let's go with 6 columns across, and we can always add as we need, okay? So you can always write this out. Remember, when you're writing, it helps engrave a neural pattern. Okay, so the type of function, we will have a linear function, also a straight line, that's a linear function. Then we'll have a quadratic function, also known as a parabola. Okay, and then you will have a hyperbola. And the last one will be an exponential function. Okay, over here I'm going to indicate shape, which we'll draw in a little bit. And then we'll create a standard form. Now, when we say standard form, it's not necessarily speaking about standard form in terms of what you see in the textbooks, but just I want to have an example here that goes through the origin without any other movements, right? Sometimes in the class, I like to refer to this as the mother graph. Okay. And then here, let's take an example. And then from the example, we move a little bit forward. We're going to move 2 units up. Okay, so this is the first transformation. We will move 2 units up in terms of that graph, and then we will move 3 units to the right. Okay. So let's start. Now, remember, in terms of a linear graph, what is a linear graph? A linear graph is just simply a straight line. So if I take a straight line, this is what my straight line going to look like, right? Okay. A quadratic graph, that's a parabola, it's going to look like that or like that. The hyperbola, remember, it's based in 2 quadrants, so it looks like that. Okay. And then the last graph that we want to show you is, of course, an exponential, and it could look like that. Okay. Or like this, depending on how it's transformed. However, at this point in time, it is only our mission to give you the mother graphs. Okay. So remember, this is going to be a straight line that's linear. This here is going to be the quadratic or the parabola. This over here is your hyperbola. Now, the hyperbola is very, very popular. It's one of those questions that when the students study, they can get 100% in it, and it comes in almost any and every matric examination. Let's hope it's the case this year as well. And lastly, over here, I've got the exponential curve. Okay. So there's our shapes. Remember, when I'm done, I'm going to draw the shape in here as well. Let's start with the standard form. Standard form from the mother graph. Let's insert an equation there. What will the standard form be, right? So here, I'm going to say y equals ax. Okay. Then for the parabola, okay, I'm going to do the same thing. Y equals ax squared, right? So that's my parabola. For the hyperbola, y is equal to a over x. Remember, it's always useful for you to write this out or to work with me as I proceed. And then for the exponential curve, we need to fix the spelling. Exponential over there, what does this look like? This is y is equal to a to the power of x, right? Okay, so we'll start with that over there. Let's just pull this down. We'll look at each of our examples there in a moment. Right, so okay, so now, okay, let's just leave the formatting like that for now. So we'll come to shape. Now let's look at an example. Let's take the example once again of y equals 2x. Now remember, that's going to be an example of our mother graph. Now the coefficient of x you're also very familiar with. The coefficient of x for a straight line graph is simply going to be its gradient. Now remember, if I have a graph and I want to compare the following, I want to compare, for example, y is equal to 2x, right? That's one graph. Let's say y is equal to 5x. Okay, that's the blue graph. And let's take y is equal to 1 over 2x, which is a half x. And remember, the coefficient of x is its gradient when it's a linear curve. And what it tells us is how steep that graph is. Now, what I want you to also note is that if the coefficient of x is closer to 0, then it would tend towards the x-axis, meaning it's going to have much less steepness. If the coefficient of x is a greater number, then it's going to tend towards the y-axis. Okay, and hence we can see the blue graph has a greater gradient or more steepness than the red graph, and the red graph has got a greater gradient than the green graph. Okay, now if we also look at an example, what is the negative x value? Y equals minus x. You can see that that's sloping downward. So we can see there's a negative slope over there. Okay. Sorry, I have to do this because some of the things are off my screen a little bit. So that's a negative graph, right? Okay. And let's say we take minus 5x. So it will still tend towards the y. So it's a greater negative value. So it still has more steepness, but it's tending towards the y. And so as you can see, we also call this, it's decreasing on this interval, because as the x gets greater, the y is getting smaller and smaller, and hence it's decreasing on the interval. Anyway, so you can clearly see the greater the coefficient of x for a linear curve, the steeper that graph is. Okay. Now let's go back to our example over here. We know that that is the gradient. So here the first transformation is 2 units upward. Let's make it 3 units upward, okay, and 4 units to the right, just so that I don't use the same number for each of our examples. Okay, so for the quadratic, once again, we'll choose an example. Y is equal to 2x to the power of 2, so that is 2x squared. Then for the hyperbola, we'll use an example as y is equal to 2 over x, right? And for the last one over here, we'll say y is equal to 2, oops, that's on me. Oh my, what happened there? Y is equal to 2 to the power of x. And there's our exponential curve. Okay, so students, what I want you to observe over here, if we go to the parabola, let's look at what the coefficient of x squared is in the parabola and what that means actually. So if I go to, if I change this to a parabola, you can see that's what a parabola looks like, and I'll put the graph on. There's my red graph. What happens when I have 5x to the power of 2? So again, the coefficient of x squared is going to be 5 in this case over here. And if you look at this very carefully, you can see that that gives us, that's also going to be steeper. So the smaller we make it, if we make it a half x squared, it's going to tend towards the x-axis, meaning it's steep, less steep, very open, right? Okay. Now, one of our teachers referred to this in a certain way, but I think that might be a little bit rude to put on air. But I suppose it may have helped some students remember how to look at the gradient and also the steepness that we see over there. There's a lot more we can say about the graph, but we'll just remember the short forms for now. Okay, moving forward, let's transform any of these things. If we take this, we have y is equal to 2x, right? So I'm going to take that graph. But let's say I want to move that graph upwards. Then I'm going to take that entire equation of 2x and I'm going to say plus 3. You see there? That plus 3 is going to be the movement that happened over here. Now, if I take the next graph, if I want to move the graph upwards, once again, 3 units upwards is going to give me that. Okay. Now, if I go and I take the next one, I'm going to add again 3 units to the entire y value. And if I do that over here, this is what I will get, plus 3. Okay, so I'm simply adding to the entire y value that I see over there. And that, once again, is fairly simple. Now, over here, same story, plus 3. Okay, now what about moving 4 units to the right? Now, when we go to migrating or moving things to the right, there's a rule that you must remember. When you move up or down, you simply add or subtract to y, okay, the entire y value. So when you move upwards, you're going to add to the y value. When you move downwards, you're going to subtract from the entire y value. When we move to the right, we try and remember this in a little bit of a counterintuitive way. When I move to the right, if I move in the positive x direction, then I'm going to manipulate x, and I do so by subtracting from x when I move towards the positive x direction. I subtract from x in the algebraic formula, okay? I do something else when I look at the coordinates. I want you to remember that. But when I'm manipulating the algebraic formula or the formula for that rule, then what I need to do is I need to subtract from x when I move in the positive x direction. However, if I move in the negative x direction, then, sorry, let me just check something here quickly. Yeah, anyway, coming back to this. If I move in the negative x direction, then I need to add to the x coordinate, okay? So remember, if we were moving downwards here, all of these signs would change to minus. Now, let's take that same example, and let's say what's going to happen when we move 4 units to the right. Okay, when we move 4 units to the right. So if you see there, that whole thing is x, okay? Now, what's going to happen over here is I need to do something. I need to subtract from x, okay? I need to do what? I need to subtract from x. Okay, so when I subtract from x, it's because I'm moving in the positive x direction. I'm going to say minus 4. So now the minus 4 over here is coming from this transformation that we're doing over there. Okay, right. So let's take the next one. Okay, let's take the next one. There's x. Now you must remember the entire x itself is squared. So when I move the graph left and right, what I need to do is I need to manipulate the x again. So I'm going to say that x minus 4. Okay, so that over there The new equation will be x minus 4. Okay. Right, so let's go to the next one quickly. Let's complete this transformation that we see over there. You see x. I'm putting it in a bracket so that you know that the x is there and we're going to manipulate that entire x. However, for this particular question, I don't need to put it in a bracket, but for the top two, I do. And if I don't put it in a bracket over here, it's very easy to see that I'm going to replace the entire denominator with x, minus 4, right? And that's what I would have over there. Okay, so students, for the last part, I have to once again replace the x. Here the x is slightly different and it may appear to be a little bit more tricky because the x is in an exponent. So if you look at 2 to the x, 2 is the base and x is the exponent. So I'm going to have over there minus 4 once again, and that's going to be my transformation. Okay, so what I also want you to observe at this point is all of these graphs that you see in the first row are the standard graphs, okay? Those standard graphs, let's just get this here. These standard graphs that you see over here, I want you to observe that that's the standard form. In other words, it's the mother graph. There's no manipulation happening there. At that point in time, it's just ax squared, a over x, a to the x, right? Here's an actual example that we now see, because when you have the equation, the only unknowns you must see in the equation is x and y, because those would be your variables. You must always have a value for your a, your x, your p, whatever it is, right? And once you have those values, there's a certain way to also find those values if you are given a graph and you need to deduce information from it. We're going to look at examples shortly. Look at all our movements upwards, look at all our movements to the right. Now, if I move to the left, then I must add to x in the algebraic formula. Remember, once again, the shape of this graph, the shape of this graph, that's going to be a straight line. Okay, I have no idea what's happening here. Let's see. Anyway, you get the idea, drawing the shapes. We've drawn it for you earlier. Okay, let's move on a little bit. Let's go through our functions recap of grade 11. Now, what can we say? What can we say about grade 11 functions that we are familiar with? We can speak briefly about the parabola, okay? And I think when we look at straight lines, we'll do them whilst focusing on examples. Okay. Okay, so what can we say about the parabola? Okay, a few things you know about the parabola. There are two forms that you're familiar with. The first form, one is called standard form, one is called the vertex form, right? And depending which country you go to school, sometimes they change the language there. So anyway, the one form will be the parabola in terms of ax squared plus bx plus c, right? And that's y or f of x. And the other form is going to be y is equal to a into x minus p all squared plus q. This form is sometimes referred to as the vertex form, sometimes it's referred to as the turning point form. Okay, now something that's important with this first form is that you immediately know, when you look at that first form, what the turning point would be. And the turning point here has coordinates, p and q. Now, if you go back to our first lesson, we spoke about negative x. Now, negative x is not negative. It's the additive inverse of x. Basically, when you add negative x to x, then you must get 0. So if you see a minus 2 over here, then the value here is going to be positive 2. If you see a positive 2 over here, like plus 2, then this thing is going to be minus 2. Because this formula here is defined with minus p, and here we have p, right? So remember, this isn't a negative. These two things are additive inverses of each other. Okay, now moving forward. Before we go into that, I want to just very quickly focus on transformations because in terms of function notation. Okay, so I'm going to bring you back here quickly, and I'm going to just quickly put on a new slide, and let's talk about transformations, right? Okay, so what can we say about transformations? Now, I want to focus on transformations just very quickly in terms of function notation. And when we say function notation, we're talking about the following. We're talking about what is f of x, okay? F of x, if I say f of x is equal to 2x plus 3, you might have started with the function y is equal to 2x plus 3. Now there's another function where the y output is maybe 4x squared. So we now might refer to the one function as f, we've given it a name, and the other function as g. G of x is equal to 4x squared. So there's two things that this helps us with. Number one is it helps us keep track of different graphs and functions by naming it. Number two, this is a little bit of a technical matter because this is reserved for function notation, which means if you're sitting with a particular map from one set to another, and that's a relation, but it happens to not be a function, grade 12s, you will know what I'm talking about here in terms of the pure definition of a function, then we reserve this notation only for functions. So in other words, not every equation like y is equal to something can be represented with this, okay? But for these two examples, they are most definitely functions. Now, why am I touching on this? You will also know sometimes students are thrown off in grades 10, 11, and 12 with what this means. If I am given f of x is equal to 2x plus 3, and I ask you what is f of 1, then you very easily will be able to tell me f of 1 is 2 times 1 plus 3. If I ask you what is f of 2, you can easily tell me it's 2 times 2 plus 3, right? If I tell you what is f of 4, you're going to tell me it's 2 times 4 plus 3. Now, what happened over here is wherever I've seen x, I throw in whatever is in the bracket, okay? So what if I tell you f of cow? Then you're going to tell me it's going to be 2 multiplied by cow because cow takes the place of the x plus 3. Okay, so that's fairly easy to see. Now when we go to transformations, let's start with our first transformation. Let's take a reflection. Let's start with some reflections, basic reflections. Okay, just hold for me quickly. Just quickly write this down, grade 12s. Okay, grade 12s, apologies for that. I hope you familiarized yourself quickly with those functions. Now, let's get into, start off with reflections, right? Now, this is a crash course here. So when we talk about reflections, let's talk about one in the x-axis, let's talk about one in the y-axis, and let's quickly go into reflection in the line y equals x. Okay, now if we talk about, let's just focus on the first two for now, and then we'll break it down in terms of function notation as well. But let's talk about a reflection in the x-axis. What does this mean? It means that the x-axis serves as your axis of symmetry, right? So if you go to a graph and you have a graph, and let's say that graph is going to be y is equal to 2x. Oh, right. Y is equal to 2x. That's my graph. This is the x-axis. Okay. Now, what happens with the coordinates? Let's say all your coordinates or your ordered pair is x and y, and it changes to x and negative y. In other words, every y value for the same x value became negative. It became the opposite y value of what it previously was. Then, in terms of an equation, you have y is equal to 2x, but y is now negative, so you make it negative. Negative y is equal to 2x. Okay. Let's just negative y is equal to 2x. And there you can see my x-axis is the axis of symmetry. And this is a little bit of a poor example. And the only reason for that is I didn't add any adjustments. So let's make that plus 3. And let's make this also plus 3. Now you can clearly see that the x-axis serves as the axis of symmetry because we've got the same image above and below. Okay, you can play around with Desmos, do the same thing with the y-axis. So as a rule, for the y-axis, a reflection in the y-axis means that the y-axis is going to serve as the axis of symmetry. And over here, you're going to get negative x and the same y. So the same y value, but the opposite x value went in. So if you type it in here, you're going to replace the x. If we look at this quickly, let's leave the y as regular y. And let's change the x that we see over there. There was x. We now change it to minus x. When we change it to minus x, we can see that the y-axis, which is this line here, right, this vertical line that we see over there, will have the same image on both sides. Okay. Okay. Okay, excellent. Right. So let's go back to the transformations. In the line y equals x, it just means that every x is now y and every y is now x. So as coordinates, this will be x and y becomes y and x. That means every coordinate swaps around. Now let's just focus on the first two. And let's talk about what's actually happening with these transformations. Okay. So if I throw an equation in here, I start off with some graph f of x. Okay. I've got some f of x. Now what's essentially happening, there's no longer f of x. I'm sitting with f of minus x. Look carefully if I describe this. Now you must be able to tell me algebraically what's actually happened over here. Algebraically, what's actually happened over here is I started with some function x. I now see that the function has been transformed, or it's changed in such a way that I actually see for every f of x that comes out, there was the same y value popping out, but the x values changed to negative x. So sometimes, or not sometimes, in your examinations, when they are testing transformations, you're going to be given it in function notation. And you must be able to say what's actually happened here. All the x values became negative. And when the x values become negative, if we go to an example where the x value became negative, but the y remained the same, that's actually a reflection in the y-axis. Okay? So we can say about this thing here that that is actually a reflection in y-axis. Okay. Let's take f of x again. And that f of x, now I've got the same f of x, but remember f of x represents the y value. It's the output of the graph. I'm now going to put the minus in front of the f. And now what you see is, well, I'm sitting with exactly the same input over here. I'm sitting with an x that went in as the argument or the input parameter, and I'm getting out the opposite of y, right? The additive inverse of y. I'm not getting out just f of x, I'm getting out negative f of x. So in other words, the y values became negative there. And if you look at this here in terms of just coordinates and points individually, I've got x and y that has now become x and negative y. So this reflection in the x-axis, this corresponds to the reflection in the x-axis. Okay, so here, reflection in the x-axis. Okay, that looks poor, and that also looks poor. There we go. Now let's take one or two more quickly. I sit with f of x. I get a new function. My new function looks like this. I've got an f of x, plus a. Okay, now let me place a restriction here. I'm going to tell you that the a itself is greater than 1. I mean, greater than 0. In other words, a is positive, right? A is greater than 0. So let's just put this here. This is a restriction. Now, why am I restricting it? Because when you add a positive number, the whole thing remains positive, right? So I'm going to say, I'm telling you that I've got a positive a that I'm now adding to this thing over here, where a is just some number. But the f of x that you see over here, once again, corresponds to the y value. Corresponds to the y value. Okay. Now, when this corresponds to the y value, and now I'm adding to y, we've done this over here. We've looked at it over here very thoroughly, right? There's my y. I've now added to y. So in other words, when a is, this number is some positive number and I've added it, I can say this was a shift, and it was a vertical shift upwards. Okay, I want you guys to understand these notations, because the last parts of these questions are always asking you, we've transformed it in some way, what's actually happening with that transformation? What can you tell me about it? What points have changed, etc., etc. Okay, now let's just say I'm adding to a, but a was a negative value, and let's assume the same thing. I've defined this as minus a, but a is still positive here because now I'm subtracting a positive number, which makes this overall negative. Okay, then this will be a vertical shift downwards. A. Ooh, downwards, right. Okay. 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 I think we'll cover a few more transformations in the next lesson as well. When we multiply the value of x, when we divide by the value of x, that sort of thing, when we subtract and we add to x, then we can also see what's happening. Let's cover that very quickly. Okay, so let's say we have f of x, right? Let's keep this as some positive number. Why am I defining it as positive? Because when I say plus a, and a is a positive, then in this bracket, I'm going to end up with x plus something, right? Then we describe this as, that's going to be a shift left or right. So in this case, horizontal shift, right? And in this case, I'm adding to the x in the equation, right? In the algebraic rule. And remember, I said when you manipulate a function algebraically and you move in the negative x direction, then you add to x. And here we're going to add to x. So horizontal shift to the left. Okay, this is the one that works counterintuitively opposite to what we remember and what we see from y. Okay, let's go to the next one. F of x. Now I'm going to subtract from a, but I'm saying minus a, but a is still positive. So when you have a minus times a positive, the overall is going to be minus, and this is going to be a horizontal shift to the right. Now, I've already covered these examples. I've done it here with you. I said if I move 4 units to the right, I'm going to subtract from x. Right. However, if I go over here, I'm showing it to you in function notation. So if they give you a question, and the question was, tell us what happened to the graph, or and the original graph was f of x equals da 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 da. Now they tell you g of x is equal to f of x plus 4. This means in your equation, you've replaced every x with x plus 4. Therefore, this thing here represents the graph of f having moved 4 units, right? We didn't subtract from x, we added to x. So we moved in the negative x direction, right? So moved 4 units to the left. That's actually what's happening. Okay. Let me know if we're together so far. Okay, we've got about 20 minutes left. We'll now spend that 20 minutes actually looking at some quick questions. Okay. So bringing us back to the questions that we see on screen and recapping things about the parabola. we've covered two forms, right? The one is the form where we can read off the turning point instantly. The other form is where we have to apply a few more things. So we start with the easier one, the vertex form. Okay. For every graph, there are certain things that will be in place for any and every graph. So what are those? The X and Y intercepts. Okay, X and Y intercepts. X and Y intercepts, any and every graph, the process of finding them will never change. Hence, if a student gets this wrong at the matric examination, it is also a criminal offense. Okay, so don't get this wrong, guys. X and Y intercept, you know the X intercept corresponds to Y equal naught, so you make Y equal naught. The Y intercept corresponds to X equal naught because it's something you know, that's how you will solve for it. Okay. Now, let's quickly go and look at this first graph over here. Also, the other thing you know with the parabola in terms of its forms, we said the one form is y is equal to a x squared plus bx plus c. The other form we said y is equal to a into x minus p all squared plus q. This thing over here, x minus p all squared plus q, right? We said this immediately gives you the turning point of p and q. Like you don't need to go calculate anything. The other form, you must still go calculate. The x and y intercepts you must calculate no matter which graph it is for any of these two. Okay, so for the first example, if I take f of x and I'm required to sketch it, is equal to x plus 1 all squared minus 9. We need to know the turning point from here, but also this a value that you see over there, when a is positive for a parabola, when a is greater than 0, you have a smiley face parabola. That's probably what your educators told you. And when a is negative, you have a sad face parabola. Okay, so for this one, we know it's going to be smiley face because in front of this here, I've got a positive, invisible by positive 1. Okay, right? So that's the shape. Then if we look at the x-intercepts, what about the x-intercepts? I'm going to make y 0. Okay, so if I make y 0, I'm going to replace this because this corresponds to y. And that's going to be 0 is equal to x plus 1 all squared minus 9. Okay, now, if we take x plus 1 all squared minus 9, there's two ways to do this. You could easily just take that over, square root both sides. Remember to add plus and minus. The other way is to actually multiply all of this out. So I've got x squared, 1x doubled is plus 2x plus 1 minus 9. And this obviously adds up to minus 8 plus 2x, x squared is equal to 0, right? So I've still got the 0 there. Factors of 8, you subtract to give you 2. And of course, that's going to be 4 and 2. So when we factorize, we're going to sit with x and x. And we're going to sit with 4 and 2. Minus 4 plus 2. And therefore, I've got x is equal to negative 2 or x is equal to positive 4. Okay. So let's just, for argument's sake, say I'm going to draw my axes in the meantime. For drawing this graph, okay, that's my y, that's my x, okay, and I'm going to indicate these 2 points in the meantime. Since I've used green, let's stick to green. That's going to be minus 2. That's 2. Then this side will be positive 4. Okay, minus 2 and positive 4. Let's just double check all my calculations here as well. No, I should be prosecuted, right? Okay, so there's a criminal error. Move your eraser faster to make it bigger. Okay, interesting. My signs are messed up there. Something felt whack. Okay, so if you look at this, it's different signs, but I clearly have to have positive 4 and minus 2. Okay, so positive 4 minus 2, this leaves me with negative 4, and this leaves me with positive 2. Okay, now let's just go erase that quickly. Okay, Let's just put that in and switch back to that green button. Okay, so -4 we'll then say is over here, and we'll say 2 is half of that, so the positive 2 is going to be over there. I've got my x-intercept. Now the y-intercept is obviously fairly simple. So for the y-intercept, you and I both know, we simply go y-intercept, and the y-intercept here, let's choose blue. I'm going to make x naught. So I've got y is equal to 0 plus 1 all squared minus 9, and that is easy to work out. So the y-intercept is going to be 1 squared, which is 1. 1 minus 9 is going to be positive negative 8, right? 1 minus 9 is minus 8. So now that's 4. 8 will be roughly around there. That's going to be minus 8. Okay. Now, the only other thing you need, remember, for any graph, it's going to be x-intercept, y-intercept. The other thing that you need, of course, is going to be the turning point, because that's what makes a parabola a parabola. It's got to turn somewhere. And obviously, this is a positive shape, so you can check your intuition. It's going to go down like that. It's going to have some turning point over here. It's going to cut through the y, and then it's going to go up there. Okay, let's work out the turning point. In this form, the turning point is very easy. It's not rocket science. In fact, it's given. Okay, so the turning point, it's going to be -1 because it's defined as p, and the function itself was defined as minus p. So if you see minus p here, you know this must be p. Okay, so the turning point is going to be -1, and the y value of the turning point is exactly what you see, because positive q is just q, right? Whether q was negative or positive, it's going to be the value of what q is. So here, q is -9. Okay, so there we go. That's -8. This is going to be -1, and that's going to be, that point over there will be -1 and -9. Okay, let's draw the graph. Fairly simple, just by joining all of those things together. Right? I just want to check something. No. Yeah, that's my parabola. Okay, I apologize for the scale, makes it look a little bit whack, but that's the parabola that we see over there. Okay, so in turning point form, very easy. You can easily tell the shape. You can easily get the x-intercept, the y-intercept. You just need to find the turning point, and voila, you're going to join everything. Now let's move on to something quickly, to the other version. And then we'll look at how do we actually get the equation of a graph if the graph is given. But before we go to that, let's go to this question of x squared minus 4x plus 3. Okay, so that's the next one that we see over here. F of x is equal to x squared minus 4x plus 3. Okay, look at that, familiarize yourself with it. We've seen a lot of it in terms of the quadratics. Once again, this here is ax squared plus bx plus c, okay, and that's equal to y. The a value, just like in the other form, told you whether the graph is going to be positive or negative. So this a, greater than 0, smiley face, less than 0, sad face. Okay, here is positive 1. So here I can clearly see a is positive, therefore it's going to be a smiley face, right, or concave up graph over there. Now, let's go and find the x-intercepts and the y-intercepts, right? So let's start with x-intercept, because x-intercept will be, make y naught is equal to x squared minus 4x plus 3. Factors of 3 I add to give me 4. We know that that's going to be 3 and 1, x and x. And you know that this is going to be negative and negative, right? Okay, so therefore, my x is equal to 1 or x is equal to 3. So on the graph that we're going to draw, right, remember, we're going to sit with some axes that looks like that. Okay, let's use the green there again. And I've got 1 over there, and I've got 3 over there. So a graph, it's going to look something like this, right? Because the turning point is somewhere here. Okay, I think that we have hit a slight snag. I'm just checking the schedule. That snag is load shedding. So let me quickly just reshare. Amir, can you still hear me?
Indeed, Brother Imaad, loud and clear.
Okay, no, awesome. Let me just reshare the whiteboard. Yeah, let me just reshare the whiteboard. I do apologize. And then we can wrap up that two questions. Yeah, let's just share just the whiteboard for now. Okay, there we go. Okay. Okay, so let us quickly draw that for what we see over here. Now, that's the x-intercept. The y-intercept is fairly simple, right? Because if you look at the y-intercept here, you will have the following, right? The y-intercept will be very, very simple because when that is 0 and that is 0, I'm only left with 3. So my y-intercept, y is equal to 3 as a coordinate. That means on the y value, I'm going to sit with 1. That's 1, 2, there, roughly 3. Okay, so I've done that in blue. The last thing I now need to do is I must find the turning point. So how do I find the turning point? Let's take you back to grade 11 once again. The turning point of a parabola, the x-coordinate thereof, falls at the axis of symmetry, right? So what is the axis of symmetry? The axis of symmetry is x is equal to minus b over 2a. It's a vertical line. And for the turning point of the parabola, it's the first coordinate is minus b over 2a, and the second coordinate, the y-coordinate, is f of minus b over 2a. And remember when we did function notation not too long ago, a few minutes ago, we actually saw that f of minus b over 2a is whatever this value is. I'm going to substitute it into the x value in the equation, and I get a corresponding y value. So let's see what the actual turning point would be. If I take minus b over 2a, remember my a value here is 1, my b value is minus 4, my c value is 3. So x is equal to minus b over 2a, that's negative 4 divided by 2 multiplied by a, which is 1. Okay? And that's going to be positive 4 over 2. That gives me a value of 2, which means that the x-coordinate, this is where 2 is, right? The x-coordinate of the turning point will be 2. But how do I find the y-coordinate? I take f of 2 now. And that means wherever I see x in this equation, I'm going to substitute in 2, right? Minus 4 times 2 plus 3. Let's work that out quickly. That's 4 minus 8 is minus 4 plus 3 is going to give me, minus 4 plus 3 is going to give me 1, right? Negative 1. Minus 4 plus 3 is negative 1. Okay, so the coordinates, the ordered pair, x and y, for the turning point of this graph is going to be 2 and minus 1, right? So my turning point is going to be 2 and negative 1. Okay, so let's keep that in mind quickly. Let's stick to purple because we've selected it. So that's going to be 2 and negative 1. It's going to be over there. That's 2 and minus 1. Now, when you draw a graph, please indicate your coordinates and your intercepts correctly, and try and have at least one point also indicated on the graph besides your x and y intercept. Okay. Right, so we've made steady progress today. We've covered a little bit of all of the transformations. We've gone over the two forms of the parabolas. In the next session, which I think we may even schedule for tomorrow, just so that we can actually finish off a sufficient portion of the functions content with examinable questions, right? So tomorrow's lesson, we will quickly go over the hyperbola, and we'll also look at the basics of the exponential. In the second half of that 1 hour that we have together, candidates, we will actually look at a few examination questions for roughly, say, 30 to 40 marks. Okay. Brother Amir, due to the load shedding, we'll cut today maybe 5 minutes short. Yeah, over to you in the studio. Shukran so much. And we look forward to seeing our matriculants in our next session tomorrow, inshallah.
Amin, inshallah. We say shukran, jazakallah khair. Terima kasih. Thank you very much to Brother Imaad Isaacs for so beautifully facilitating today's session. Cut short by 5 minutes due to the usual impediments of load shedding we're experiencing in our country. I always refer to it as the Giles load shedding. May Allah Ta'ala protect us. And I sincerely hope that as our matriculants are preparing for the examinations, Brother Imaad indicated that load shedding cut this short, but of course, load shedding impacts our matriculants preparing for the exams as well. So just as a reminder, once again, to all of the matriculants out there who are preparing for your examinations, may Allah Ta'ala grant you, God Almighty, grant you all the success for your exam preparation. And I hope that these hindrances of load shedding and whatever else comes your way will not deter you from successfully preparing for your examinations, inshallah ta'ala. To all of you, our beloved viewers, we thank you very much for tuning in for today's session. As Brother Imaad indicated, inshallah, we will take up the next session, inshallah, to continue on this particular subject. And inshallah, we will be keeping you posted each and every day on the VOC's Instagram page as well as the VOC's Facebook page as to what the next session's details will be, inshallah. It is every day at 5 p.m. And inshallah, for today, we will be ending this session. Once again, I would like to say shukran. Thank you very much to all of you, our beloved viewers, for tuning in. I hope you have benefited greatly. Just as the smiley faces are here on the screen of the various functions, I hope that you are smiling there at home as well as you prepare for your examinations. We thank Brother Imaad for facilitating, and inshallah, we will take up the rest of the sessions in the coming days, inshallah. Please, a reminder once again, in conclusion, to all of our matriculants out there, please share this link with your fellow students, your friends, your colleagues who are doing mathematics, pure maths, as we would say, who are preparing for the trial examinations, as well as the NSC examinations. Forward and share this link to them. And to all those who are not in Matric, but you have family members or friends who are in Matric, please share this link with them in order that the matriculants may prepare adequately to be successful in their trial examinations as well as the NSC examinations, inshallah. From our side, we say shukran and thank you very much to each and every one of you. Until we continue tomorrow with the next session, we say assalamu alaikum wa rahmatullah.
Thank you very much, Chief Whip of the Inkatha Freedom Party. Let me also take this opportunity to thank all the leaders of various political parties. In particular, Honorable Ndlozi, thank you for that message. It has really pained us that those who have not lifted a finger for South Africa wants to sully the legacy of Mfuna Papingangeni. Those who knew him knew him as a man of peace, a great man, a great statesman, a great South African, and we will protect his legacy. May I now call on Reverend Zondi as a
Carter and then of the INC are too numerous to mention.